Hi everyone, it's me again, coming to you from my closet. And today's lesson is dynamic equilibrium. So hopefully at this point you've completed the little activity with the 100 items that you did not put back to eat because you have handled them. And now we're going to learn a little bit more about equilibrium. So here's what it is, and you just saw this. It's a balance between the forward and reverse processes occurring at the same rate. So they keep exchanging at the same time. So when something is at equilibrium, it looks like if we were looking at this reaction in the classroom in a beaker, we wouldn't actually see any additional changes going on a macro scale. But if we were to use a powerful microscope, we'd actually be able to see a change in particles. So reactants becoming products and products becoming reactants at the same rate indefinitely. So imagine it continuing forever. So on page 427, figure 3, this is some evidence of equilibrium and how we know it actually exists. So basically what they did is they did an experiment where in a test tube, they put in some iodine aqueous, and then they supersaturated the solution. So they kept adding iodine until it would not dissolve anymore. And so they also had a pile of iodine crystals on the bottom. Then they added some radioactive iodine. So we're going to put this with a little star. This is our radioactive iodine here. That's a 2. Yeesh. And they added some radioactive iodine, and if nothing was happening, then they would see the exact same outcome when they looked at the iodine after a certain amount of time. What they actually found was that there was still some iodine up here. There was still iodine down here. But some of the radioactive iodine that was just put here was actually also in the solid phase. So it had actually recrystallized, and it was in a very particular proportion. So what this meant is that some of this iodine had actually gone into the solid phase, even though it looked like nothing was happening. They also did this experiment in the reverse, where they started with just iodine here, and again, over time, it also went into the aqueous phase, and it was in the same proportion. So this is some of the proof that we use to figure out that on a microscale, things are actually changing, even though it doesn't look like it from our point of view. So some things to remember about equilibrium. First of all, not all reactions are equilibrium reactions. So we've only seen reactions with one-way arrows at this point, but with dynamic equilibrium, this is a two-way arrow. So reactants become products and products become reactants. Equilibrium does not mean equal amounts of molecules on each side of reaction. So again, we saw this with our activity. Equilibrium doesn't mean 50 reactants and 50 products. It just means that the amount on each side stops changing. But that can be in any proportion, 80 and 20, 10 and 90, whatever it happens to be. Equilibrium can be reached regardless of the starting point. So if we had done the experiment that we did earlier with 100% products, we still would have reached the same equilibrium point. We could have started with half and half, so 50 for reactants and 50 for products, and we would have started the exchange process, and we still would have reached the exact same equilibrium. So equilibrium knows where it wants to be, and it will get there if we don't tamper with it. We also saw this in our activity. An equilibrium can be disturbed, but it eventually will form a new equilibrium. There are ways to prevent equilibrium from occurring, to continuously push it. We'll learn more about that later on. So types of equilibrium. Sorry about this. When I transfer things from one type to another, they don't always go well. So first type of equilibrium, we're going to be doing 2 lessons about this one mathematically right at the end of this particular unit, and this one is solubility equilibrium. So this is specifically for things dissolving in water typically, and again the particle exchange that occurs, and this particular phase is the ion phase and the solid phase. So this is what solubility equilibrium is all about. So a really good example of this, I'm going to fix my arrows. You would have seen me give you this tip. You can do it like this. You can also do it like this. A two-way arrow like this, doesn't really matter. But we have two-way arrows. These are ions, so these are actually superscripts here. And it shows it better in the picture down here. But basically, we have created a supersaturated solution. You can do this by either creating a precipitate or by taking something that usually likes to dissolve and just adding way too much of it. So we have this pile of sodium solid at the sodium chloride solid at the bottom, and we have these dissolved ions of sodium and chlorine up here. And when we have a supersaturated solution, it just looks like a pile of salt in some water that looks kind of cloudy, but in actuality, there's a continuous exchange of particles going on. So we don't actually notice this exchange of particles, but it's always consistent. And this will keep going like this indefinitely unless we alter or disturb the equilibrium in some way. So this is called a solubility equilibrium because it's between solids and ions. The next one is a phase equilibrium, and the reason why we have like a Coke bottle here is again because of what's happening. So this is between a gas and a liquid, and again it's just exchange of particles that continuously occurs, and this one you can probably relate to. So think about the sound that happens when you take the lid off a pop container like this. It makes this little sound, right? That's your gas escaping. What you just did is you actually disturbed the equilibrium. So when Coke, let's say, is made, at the Coke plant, they would take carbon dioxide gas and they would force it into this liquid. Now, it doesn't really want to be in the liquid phase. And so in this little space at the very top, once it's sealed up, that carbon dioxide has an opportunity to go into the gas phase. Again, this is where your equilibrium will actually take place because some of the gas will dissolve back into the liquid phase. Sorry, I'm going to fix this. This should be, whoopsies. That should be aqueous down here, my bad. And so right now there's an exchange between aqueous and gas, and this will constantly happen. But as soon as you take the lid off, the gas goes out and you've destroyed the equilibrium temporarily. Let's say you pour yourself a glass of Coke and then you put the bottle back into the fridge. Ooh, nice bottle. Ooh, I'm such an artist. And now it has a lower level of liquid in here. We still have the same components. We have carbon dioxide aqueous down here, which makes your pop fizzy, and we have carbon dioxide gas here, but we have a whole lot more space at the top now. So there's actually a different equilibrium. There are more particles now in the carbon dioxide gas phase than in the liquid phase, and this is why after a while your pop will end up becoming flat because there's more carbon dioxide gas and less carbon dioxide aqueous, and it's the aqueous part that makes it fizzy. Same thing, if I were to take the lid off and I never put it back on, I would break the equilibrium. So instead of an exchange of particles, because the gas can go out, it will continue to go out and I won't form an equilibrium at all. So that is sort of taken care of here, and again that double arrow needs to go in, and once again our subscripts don't work with this program, but you can figure that out for yourself. The last type is where we'll spend most of our time, and that's with a chemical equilibrium. So this is a chemical reaction that's taking place. You'll notice the other two reactions, it was the same particles, only different states. This is where we actually have reactants and products as totally different ingredients in both cases. And again, because we have this equilibrium, the thing about an equilibrium is that we never make 100% products. So if you're in industry and you're trying to make something for your client and you have an equilibrium type reaction that you're working from, there is some hurdles that you have to overcome because you'll never make 100% product, which means you can have a lot of waste. So there's different techniques that we can use to overcome this, which we'll explore later on. In the next several lessons, we'll get into some of the math of how do you figure out how much you can actually make at equilibrium if you're not going to make 100%. So these are the questions you're going to try. This should be a little happy face, of course, because everyone loves to practice. And as usual, there will be a homework request Google Doc that you can ask for some questions to be taken up, and then you'll get to hear my lovely voice again as I talk you through it. Have a great day, folks. Bye-bye.